And now, the action potential. Here we go. So, just to go back to the preview we looked at last time, remember, first we have to add up the graded potentials, all right? Then, if we exceed threshold, that's going to open the voltage-gated sodium and potassium channels. Sodium comes through first. That depolarizes. Then the sodium channel is closed, potassium channel is open. Potassium flows out, repolarizes. So much flows out that we hyperpolarize the membrane and we go down lower than -70. And then, thank goodness, within a matter of microseconds, the sodium-potassium pump will restore the concentration and electrical gradients. All right? So here we are first. The resting potential, the resting state, all right? The inactivation gate of sodium is open and the activation gate is closed. So this is, I said before, sodium voltage-gated sodium channel is kind of peculiar. It has two gates. So look in the picture. See how the potassium gate channel has only one gate? Sodium has two gates. On the sodium channel, there's what's called the inactivation gate, which is normally open, and the activation gate, which is normally shut. If either one of those is shut, then sodium can't get through. Both of them have to be open before sodium can get through, okay? So voltage-gated potassium is closed, all right? Voltage-gated sodium. Sodium can't get through. The inactivation gate is open, but the activation is closed, all right? So the sodium-potassium pump has pumped the sodiums out, the potassium's in. We have both the concentration and the electrical gradients. The resting membrane potential is at -70 millivolts, okay? So you can see in the upper right corner there of that graph, we're still where it's dark. We're in the dark portion of the graph. We're at the resting membrane potential, okay? What happens next? Depolarization. So they kind of leave out the step that comes next. That's where the graded potentials push us to threshold. They've left that out. And now here we are, we've hit threshold, okay? Look what happens at threshold. Look in the illustration. The activation gate for sodium now opens. What happens when the activation gate opens? Well, the inactivation gate was already open, so that means both gates are open. So now sodium comes flowing through the channel, okay? That depolarizes the cell as it rushes in. Remember, sodium opens first. Sodium rushes in, depolarizes the cell, all right? That's what we're seeing here happening. Now, within a few 10,000ths of a second, the inactivation gate shuts. Remember, the inactivation gate is normally supposed to be open, but the inactivation gate now shuts. The activation gate at this point is still open, but it doesn't matter. If either gate is shut, then sodium can't get through. So, once again, back up. What happened here? We hit threshold. The activation gate opens. Sodium starts rushing in, right? We're going to depolarize the membrane, but immediately that inactivation gate is going to shut, all right? Only about 20,000 sodiums come through. 20,000 might seem like a big number to you, but there's millions and millions of them out there. So 20,000 is actually not very many. But just those 20,000 that make it through push the membrane potential all the way from -55 up to +30 to +40, okay? That's the depolarization. What happens next? So look in the graph, where now the depolarization has brought us all the way up to the point, to the top of the graph. What happens at that top, at that point? Well, this is where the sodium channels close and the potassium channels open. So look at here, we've got that inactivation gate is shut. So notice the activation gate is still open, doesn't matter, and the inactivation gate shut, so now sodium cannot get through. But now look, potassium, the potassium gate has opened. So now potassium is flowing out. See, potassium was inside mostly because of the sodium-potassium pump. It's now flowing out. So what's that going to do? It's going to make the membrane more negative because positives are leaving the inside. If positives leave the inside, that means the inside's more negative, all right? So the potassium was much slower to open. That's why it's happening in sequence like this. The sodium's already over and done with. It already opened and shut. Now the slower potassium channel is finally opening, okay? Just as those inactivation gates are closing, potassium opens. Sodium can't get in anymore, so therefore we're not going to do any more depolarization. Now we're just going to repolarize as all that potassium flows out, okay? And what happens next? Well, the inactivation gate finally opens again, but now the activation gate has shut. So now the sodium channel is getting back to its normal state, okay? Potassium is flowing out, repolarizing the membrane, so much that we go down to like -90. We hyperpolarize the membrane. We go too negative. We go past the resting membrane potential of -70 all the way down to like -90. So again, the inactivation gate is now going to open again. Sodium goes back. The activation gate closes. So now the sodium is going to return to its normal state. Okay, that's what we're seeing here. And potassium channels close. The sodium-potassium pump will eventually return us to the resting membrane potential. How did we get back there again? The sodium-potassium pump. Pumped all the sodiums back out, pumped all the potassiums back in. Now, there was that brief period of time during which the sodium inactivation gate was still open, and I mean that the sodium activation gate was still open, the sodium inactivation gate had shut. Well, that's not the normal state of the channel, all right? The normal state of the channel is that inactivation gate should be open, all right? So it takes a little while for it to open back up again. During that period of time, it's not possible to have another action potential. Until the sodium channel returns to its normal state, we cannot have another action potential. That is called the absolute refractory period, all right? During the time that the voltage-gated sodium channel is returning to its normal state, that the inactivation gate is going to finally open again, the activation gate is going to shut. During that brief period, we cannot have another action potential. That's the absolute refractory period. Even a very strong stimulus is not going to help because that sodium channel is not returned to its normal state. It can't function yet, okay? Inactivated sodium channels have to be returned to their normal state before they can be reopened. That's what's going to limit how many action potentials we can have. Because it takes a finite amount of time for that sodium channel to reset, turns out you can't have more than about 1,000 action potentials per second. It's interesting because that sets like an upper limit on human performance. You go back to like the 1900s, people when they ran the mile, the world record was still over 4 minutes. People wondered if anyone would ever break the 4-minute barrier, and people finally did. And now people can run a mile in like 3 minutes and 50 seconds or something. They're way under 4 minutes. You might think, eventually they'll be able to run a mile in 3 minutes and 2 minutes, and then in 1 minute. And no, that's not going to happen. The reset cycle on the sodium channel is going to limit the number of action potentials that are possible. So there are fundamental, hardwired limits to human performance, okay? So at this point, even when the sodium channel returns to its normal state, so the absolute refractory period is now over, okay, we can have another action potential, but we're down at like -90. We're at 2 negatives. So instead of just having to go from -70 to threshold, we've got to go all the way from like -90 to threshold. So that means we have to have a bigger stimulus, what we call a suprathreshold stimulus. So that's the relative refractory period. Okay, 2 refractory periods. Absolute cannot have another action potential. That's because the sodium channel has to return to normal. Relative, we can have an action potential, but we're so negative it's going to take a super strong stimulus, a suprathreshold stimulus to get us there, okay? So here you go, all in one big picture. Resting membrane potential, -70, depolarization, -70 to +30, repolarized, +30 back to 70, 2 negative actually. So here's just another picture that shows that. Use different pictures, work through, follow through the graph and the pictures at the same time. That's a good way to do it. And then the propagation of the action potential. So we say that it propagates. This is a positive feedback loop. All right, so let's think about what's going to happen. So look on the left side. We've got that green tube. That's supposed to be the axon, okay? So notice where there are the red areas where an action potential is in progress. So we are depolarizing the membrane. Well, when we depolarize the membrane, positive charges come inside, but the positive charges can like flow everywhere once they get inside. So they're going to flow down to the next segment of the axon membrane, and they're going to depolarize that segment as well. All right? And when they depolarize that segment, that's going to cause the voltage-gated sodium channels on that segment to open. And then when they open, they're going to let more sodiums in, and that's going to let the sodiums come through, and then they're going to flow further down the membrane, and then they're going to depolarize that part of the membrane. Do you see? This is a positive feedback loop. As each voltage-gated sodium channel opens, it's let sodium in, which then depolarizes the next part of the membrane, which then opens those voltage-gated sodium channels. And that's going to keep going and keep going and keep going until what? Until we get all the way to the end, where we then finally release the neurotransmitter, okay? So that's the positive feedback loop. That's called propagation. You can see that in the bottom right. As the sodium comes through, it depolarizes the next segment of the membrane, and then that just keeps propagating itself down the axon. Okay, so here's just another diagram trying to show the same thing. Each sodium channel depolarizes the adjacent membrane. That lets those sodium channels open, and then on and on and on. It's like those dominoes. Like you see those, things that people set up. Once you tip the first domino, all the rest of the dominoes go. That's what's happening. It's a positive feedback loop. Once that first voltage-gated sodium channel opens, it's going to open all the rest of them, all the way down the membrane. One domino is going to hit the next one, then that's going to hit the next one, that's going to hit the next one, and we open all of them until we get to the very, very end. Okay? So, did this all make sense? Let's see. 4 of these statements are true. 1 of these is false. Let's see if we can figure out which one is false. So A, depolarization pushes the membrane potential towards threshold. B, the absolute refractory period is caused by a delay in the opening of the sodium channel inactivation gate. C, following an action potential, the resting membrane potential is restored by the sodium-potassium pump. D, the opening of potassium channels causes depolarization of the membrane. E, potassium channels open more slowly than sodium channels. Which one of those is wrong? Yeah, it's D. Potassium channels hyperpolarize. Sodium depolarizes. Potassium hyperpolarizes. Okay, so one last slide here. We've talked a lot about graded potentials and action potentials, about how different they are in so many ways. Sometimes people still confuse these a little bit, so let's look at all the differences that we've seen between graded potentials and action potentials, okay? So the origin. Graded potentials happen on dendrites and cell bodies. Action potentials only start at the trigger zone of the axon hillock. The types of channels. Action potentials are produced by voltage-gated channels. Graded potentials are produced by ligand or mechanically gated channels. Conduction. Graded potentials are localized, they're not propagated. They last only as long as the stimulus is there. Action potentials propagate. That's the positive feedback loop. Once you start it, it's going all the way to the end. Amplitude. Action potentials are always the same, the all or none. Every action potential is exactly the same, but graded potentials are bigger or smaller depending on the strength of the stimulus. Duration. Action potential is always the same. It starts in the axon hillock and it goes all the way to the end. That will always take the same amount of time. Graded potentials will last as long as the stimulus is there. So, if you put a burning match on somebody's arm, that's going to create graded potentials. If you take it off, then they might stop. But as long as you hold the burning match on someone's arm, and don't ever do that to anyone, for heaven's sakes, the graded potentials will continue to happen as long as that burning match is there. And then refractory period. Action potential has a refractory period, 2 kinds, absolute and relative. There's no refractory period for graded potentials, okay? So there you go, peeps. That's the action potential. We have talked through neural transmission.